discussion on an overview of the CATS device and how this thing actually works, because I was a perfusionist 28 years. I used most all the autotransfusion devices on the market. I had a company and I wanted to save money, so I got certified on working on them. I got an engineering background. So I saved a bunch of money, but I think it's really important if you use a device, you understand at least the basics of how it works and then the technology behind it. I see so many people that are button pushers, and that frustrates me because it really helps you in the long term on troubleshooting, because you are going to have issues no matter what kind of device you're using. Which one is here? I should put my glasses on. I'm really fighting the old eye thing. Everybody out there is bowl-based. They fill, wash, empty, bowl size. They do things a little bit differently. You probably noticed a few of these. The one down the bottom left there, that's the Brat 2, which is going away. But I used most all of these. They all do a nice job. Our technology is completely different. We're the only people that uses a continuous flow technology. And hopefully after this you get a better idea of how that works, so you can make a educated decision on what you want to use in your practice, or even a trial device. I work for the manufacturer, Fresenius Kabi. Terumo is our distributor here in the United States. We provide field service for the most part. We have some people do get certified on it. I am certified to work on this device. I don't work on it. I help out. I work very closely with our field service people and the marketing and sales people, which they're trying to turn me into, but I want to keep that clinical hat. And I am the clinical educational support throughout the United States and Canada, so I train Terumo people and to go to customers and answer questions. So if you ever have a question, feel free to contact me. I'll be out running around. There it goes. As I said, we're the exclusive manufacturer of this continuous flow technology for the CATS device. We do three things at once: bowl systems, fill, wash, and empty, and then do it again. Once we fill our chamber with 30 to 50 cc's of packed cells that's in the chamber, we will then continuously fill, wash, and empty, and keep that going until we're out of product or salvage blood. These are some schematics. We have 4 tubes that go in and out of this chamber. 3 of them have pumps, 1 doesn't. That's the waste port. And then there's another schematic down there. I'm going to show you in depth each series or phase on how this chamber works. I went over to Germany and I got trained on it, and I was calling it a disc. And I don't know if you work with German engineers, but they're extremely dull and boring and very proud of what they do. And it's not a disc, it is a chamber, a processing chamber. So, but I learned a lot from these guys. They were extremely knowledgeable. We do get out 99.9, we used to say 100%, but the FDA won't let you say 100. It's not, it's 99.997 or something percent of the non-emulsified fat in all our programs, and I'm going to tell you how that works. We get a hematocrit of 60% or greater. How many people out here use a CATS device? And you know that when you bring in a low hematocrit coming in, your crits are, what, 70s, mid-70s? Is anyone? And you can actually get close to 80 if it's really low. So, features, so a little overview of our new device. We had our old device, which was the yellow top. This one's updated significantly. It's an adjustable, I think I'm missing a slide here. It was weird. Did I jump back? Never mind. So we made it more usable friendly. We talked to perfusionists and got input through all over the world. the height is adjustable, so the whole body of this goes up and down 5 different levels. So if you're sitting next to the pump, you can set it down. Or if you're standing up and you're an ogre like me, it's really high. And then we also decreased the noise. That was probably the #1 complaint on our old device. We brought it in and it sounded like it was taken off because this umbilicus is flipping around, and we had a lot of people just say, surgeons, turn around, get that thing out of here. We don't want to ever see it again. And then it made weird noises too, but we'll talk about that. So it takes 3 of our new devices to make the sound of our old device. So it's significantly quieter, and I was really impressed when we brought it in the OR the first time. So that was a nice change. Our lid on our old device, you had to slam the thing and push it down. And this one, it reminds me of my dad's old Cadillac trunk. You push it down and it pulls it down and hold it in nice and smooth. So it's a little more precision. We have a large touchscreen, biggest touchscreen on the market for an autotransfusion device. It's maneuverable. You can flip it around back to either side. You can use gloves on it. And while I'm thinking about it too, one neat thing they did is on the device, everything that is dark blue is a user touch point. So you can see that's the lid, the handle, the IV poles, and you can look at it over in the room, the next door room. It's over there, you can see it. Even the buttons on the display are dark, that has a user function to it. Oops. Sorry, I'm having finger problems here. We also added hematocrit sensors. So it has an incoming hematocrit sensor and an outgoing hematocrit sensor. So then you can see that the device is concentrating and doing what it's supposed to do. The first question I get as a perfusionist is, can we use this for quality control? They are not validated for that at this point. I can tell you that they are very accurate, but you have to understand what they're doing to use them if you want to validate them yourself. But I have to say it is just a monitoring device at this point. We then have an auto start feature. Most all auto start reservoir holders on the market are weight based, so if you lean on it, it kicks in, or you push it up against something. This is an infrared array on both sides, so it's looking at red cells, and it won't kick in if it just has saline. So you put your number in there, whatever, between 200 and 3 liters, it'll automatically kick on. You can always press the manual start, and it'll start processing. So that's a very reliable way of measuring that. We do have an optical integrated vacuum pump source in the base of the unit. It's down there at the bottom, a little blue dot. When we first came out, we had the intelligent vacuum suction, which means it has to sense resistance and then it'll ramp up and get to that set level. A lot of surgeons don't like that second or delay. So we have now a manual setting that's going to be set right at whatever you want, and it can stay there. And we also have a default setting to where you can set, when you turn it on, it'll set at 100 or 150, 200, whatever. I've seen this, our range is only 100 to 300. I've seen ORs, as you all know, wall suction can be 600, 700 people I see. 300 is the highest we go. We do have an installation guide. I realize perfusionists don't look at installation guides, but it is there and it's very handy. It has pictures. That's a picture of it going up and down with a knob on the back that adjusts the gas shock. It has 8 pictures of installing the software, so you can do it step by step, and then words to go with each picture. Now I want to talk a little bit about the chamber technology and how this chamber actually works. This is a picture from our field service computer. It was from a field service technician. This is what they look at on our camera. That is the brains of our device. This controls all the pumps. It looks at the interface between the red cells and the plasma, the buffy coat. This is not something you would see clinically, but this comes from the technical of the side. And this camera is 7 times the resolution of our old camera. So the old device was brought into the US, it was 1994. I had a slide I'm missing somehow, but in 1994, and that was the CATS Classic, and then the CATS Plus came out in like 2004 that they updated that, and then the CATSmart came out in the US 2016, end of that. So 2016 and 2004, that's a huge jump in time. It was a long time coming for an updated device. So the cameras and all the technology is significantly better and improved. With our device, we have really low centrifugal forces. Even though it's a larger diameter, we flow at about 2,400 at the most, but our centrifugal forces on the blood are about a third of competing devices. We have 3 pumps doing the job of 1 pump. This gives the illusion that we're really slow. I don't know how many people always say this is a great pediatric pump or device, but we're not going to use it we're afraid it's not going to keep up. I always like to do the tortoise and hare scenario. We can produce, on our highest speed, 100 mils a minute of product, of PRC coming out. Granted, the reservoir is not going to drop really fast like a bowl system. The bowl system is going to drop that and stop into wash, and then it's going to drop and empty, and then it's going to drop again when it starts filling again. Ours is continuous. Like I said, it's like the tortoise and the hare. We will catch up, and at the bottom, depending on the hematocrit we're processing, we're as fast or faster. So 3 minutes, we have 300 cc's. So that's pretty fast. And our product quality does not decrease at all on high speeds. I'll show you our data. We have a Sealless centrifuge. Our disposables, all bonded tubing and plastic. There is no friction surfaces. And on this chamber, as there's a schematic of it, sits on top of a rotor that spins. So this rotor is spinning, and on top of the rotor, the chamber is suspended, and that spins at twice the speed. On the bottom, I can't see it from here, but it's green. That's the camera looking up at the chamber at a certain point. We call it the detection window. That's where it's looking for the interface and controlling everything. The yellow on the top is a infrared light that shines through the chamber, so it can see the actual and visualize the interface. So years ago, when I was using this device, I had 13 of these. I wanted to know how can they spin something that's all hooked together and not have that umbilicus rip right off. And Germany sent me this, Terumo back there too, and they sent me this picture up in the right-hand corner there, and it didn't make any sense to me. I went over to Germany and got trained on this device, and I had a German show me. I give this demonstration now with the piece of tubing, and it made sense to me. I had to actually see it. But it's used in a lot of other different manufactured blood processing devices in the blood bank. It's another thing you can refer to is the cowboy's lasso. His hand's going twice the speed of what the lasso is going on the bottom, and as it goes around, it unwinds and winds and unwinds as it goes around. I drew this schematic here, so that's the centrifuge rotor on the bottom spinning. That outside 4 tubes was the umbilicus that goes around, is hooked to the chamber. That's spinning at twice the speed, hooked to that chamber and flipping around. A little confusing, but if afterwards you want me to show you this demonstration, it makes a lot of sense. This is a picture of the rotor with the rotor cover being removed. I'm going to show you what's under there and how this works. So that's on the left-hand side, that's the bottom of the chamber. You can see a ridge there and then some area for the teeth, tooth rotor to hook into. So that sits on top of the rotor that's on the right-hand side there, and there's these guiding rollers that spin and have a little ridge that hook into where that arrow is. So they come in on a cam and hooks it and suspends that rotor, that chamber on top. So we have the rotor spinning on the bottom and then driving the chamber on the top at the same time. So now we know how it all kind of mechanically works. How do the red cells move through this chamber and get pulled out to be a wash-packed red cell? Again, a schematic here, 4 tubes, 3 of them having pumps. The waste tube does not. Blood comes in from the reservoir. The one thing you have to remember, we're looking at centrifugal force. Everybody uses centrifugal force to separate the blood into its components. So as the blood comes in on the inner area and then immediately separates, it's kind of like those, what do they call it, tilt-a-wheel or whatever, all the people going flying out. Same thing. And then saline is being pumped in at the same time, and then the waste is coming out as we're pulling in more and more red cells and pumping out plasma, and then the PRC comes out at the very outer end at the highest centrifugal force area. I'm going to go over this a little more in detail as we go. I hope I don't put you to sleep on this, but as a perfusionist, I kind of like the nuts and bolts and understanding how things happen. But this is the different phases of the wash chamber. We prime our chamber. Why do we want to prime it? Well, when the blood comes in there initially, it's better to be suspended in a fluid to separate and get washed more efficiently than stack up and slowly trying to get to that point. We also use the fluid in our CATSmart to zero our transducers for the hematocrit sensors. That's a 0 point. So after we prime it, then we have the first separation phase when the blood's coming in, packing in red cells, and the plasma is coming out. Then we have a washing phase where the saline is coming in. I'm going to show you why our washing is so much different than a competitor's. And then we have our second phase is where the camera's watching this interface and pulling out the red cells when it gets to the full point. So each one here, the first separation phase, this is a close-up. This is a waste port. Red cells coming in. When they first come in, they pack extremely tight to about a hematocrit of 80%. And we keep on pulling more red cell, or the salvage blood comes in, and we start packing more red cells, and that plasma comes out. And this is the point where our non-emulsified fat is removed, because fat's the lightest component in the blood. So I think next slide will show that. Oop. So the fat, because it's the lightest, comes out first, and it goes into a part of the chamber called the balancing chambers. And they put those in there when they first designed the chamber to balance it when it spun for the weight. And when they started playing with it, they realized all the fat was being collecting in there. So we're collecting the fat and separating it by the specific gravity. We're not washing it out. On the top there, that's what I call the linear view. Our chamber is a double spiral. So if you take that and you straighten it out, and you look at the centrifugal force, you're looking down at it, the centrifugal force pushing down, so the blood's going to come in. On the right-hand side there, everything lighter goes out into the waste port, plasma, fat. Red cells march down, come to the saline port. Saline resuspends those red cells that were packed at about 80 to about 15 to 20%, then pushes that saline retrograde, or the waste retrograde, up to the waste port. And then on the other side is mostly saline, residual plasma. No one gets out 100%. We get out very high 90s. And then red cells, the camera's looking at the end, and plasma and the red cells come out. This is a picture of the actual chamber, probably used after a orthopedic case with a lot of fat, bone marrow. I'm from Kentucky, so I probably got a lot of that Kentucky Fried Chicken fat in there, and we have real good demographics in Kentucky. So we have the smokers, bourbon drinkers, Kentucky Fried Chicken, and not to mention the too close relatives. But So this is the washing phase, which I told you was a little bit different. Notice the channel is the whole width of the chamber, and we actually go straight through the pack and resuspend it. And with the bowl systems, for the most part, they have to wash up against the hard pack and try and create turbulence to get a good mix in there. So you can see the difference in that. The second separation phase, this is at the end of the chamber where the camera is looking at that detection window and the interface. And when it gets a full point that is adjusted by field service people, then we pull out that clean PRC product. This is kind of like putting it all together. This is looking down at the chamber. Blood comes in, goes around on the inside part of the spiral. You see the green, that's the plasma coming out. Keeps on going around, hits the saline port. Saline port pushes saline both directions, but retrograde is pushing back saline contaminants back into the waste port, so the waste port sees plasma from one side and saline and waste and plasma from the other side. It's hard to see on this, but I took a picture of this with a strobe, and you can actually see that I actually wanted to see it with my own eyes, that was really happening. And you can see the change in color on the top. You can see the waste port is that like triangular port, that it's mostly saline coming back from the one side. But you go back to the saline port, going antigrade all the way around. At that point, it's mostly red cells and saline going down the detection window where the camera's looking. So, if you still don't get it, I got one more slide. So this is the linear view again coming in. Basically, what I want to talk about on this is our blood flow adaptation. So you have this varying hematocrit coming in, and then you want a fairly consistent hematocrit coming out. The camera is controlling the blood pump coming in and the blood coming out. So the PRC pump coming out and the blood pump. And so as the fill level gets filled, it's maximizing the inflow. As it's filled and it starts removing, it'll then maximize it even more or decrease it, trying to maintain that. So that's our blood flow adaptation. The saline pump is on a ratio to the PRC pump, depending on the program you're using. We are very good at salvaging everything that comes into the device. We call it the safe Final PRC. So your reservoir is empty, you're done with salvaging blood. You want to process what's in that chamber. So you just hit this and it'll wash that and chase it up in the reinfusion bag. So there's very little blood left in the device itself. So we don't have to worry about partial bowls. There is no partial bowl. Washing programs, our old device had 6. We decreased it down to 3. We may increase it in the future. But I want to, people that use our device say it uses a lot of saline. And I always tell them, well, use emergency wash. They named it emergency wash, and I wish they didn't. I wish they had named it high flow wash or super wash or something, because our emergency wash product is, we have data, is as good or better than most competitors. And each one of these programs gets out 100% or 99% of the fat. I'm going to show you the data on the emergency wash. Smart wash, super washout rates. Low volume wash is optimized for lower volumes coming into the chamber. It kicks in a little sooner. It's a little slower, but you can then optimize red cell salvage for like pediatrics or ortho or something. So this is our 510K in vitro data. In vitro data with our device is worse than real life data. Our in vivo data, clinical data, you're going to see better numbers than this, especially on the hematocrit, because you don't have a standard hematocrit of 20 coming in or 40. It's up and down all over the place, so you have that adaptation creating a higher hematocrit. You notice in the emergency, and this is in vitro, it's 57% running at the max speed of our device. you're actually going to see higher than that in real life. One of the major questions I get from clinicians is on quality control. Because our device will routinely get hematocrits above 70, that concentrates a lot. So that residual plasma component is smaller. So if you have a certain amount of potassium, let's just say potassium because everyone looks at it because it's easy to test. You have potassium in a milliliter and you have potassium in 10 milliliters, and you put the same amount in both and you send it to the lab, the numbers are going to be different, right? Because the concentrated ones, even though it's the same amount of potassium, is going to say higher. So you always have to look at elimination rates. We want to know in QC what our device is doing and make sure it's maintaining the same amount of elimination. So you have to do elimination rates. This is what you send to the FDA to validate your devices and everything. Unfortunately, you have to measure 6 things. You have to measure the blood you're processing and the blood that was processed. So I can give you more information on this, but I just wanted to make the point that looking at just an N number tells us very little about what the device did. You have to know what you're starting with and what you ended up with. Another problem I see in quality control is people using the iStat or devices like the iStat. It's a good device, but it uses conductivity to measure hematocrit in a whole blood sample. This is not a whole blood sample. This is a sample with very little plasma component. Plasma is the conductive portion of this algorithm they use, and the red cells are the insulates more. So the higher the hematocrit, the more the results are skewed. That's why they have that number. I don't know, a lot of people use iStat here. Anybody? So you put that number in the CPB number to get a little fudge factor, because when you go on pump, it dilutes it a little. So send it to the lab. You're going to get a better number and more accurate. A little bit of non-continuous. All the manufacturers now, or most of them, have come up with a fat removal program because they realized they were concentrating the fat in a bowl. They can't get past that spacer because remember, the fat's the lightest, so it's just going to hang right as soon as it comes in on the lowest centrifugal force area, and it's hard to get it through there. So they came up with a program that gets rid of this fat, and they do it in different ways. And it does a really good job, but you have to choose that program, and they're hematocrit dive bombs. So why would you have to, I always want the fat out of there, because why would you want fat? Because it whips up and you have neurological issues and everything. So this is just a little schematic of bowls, how the fat hangs down the bottom. It actually hangs more even by the straw in the center. And then the hematocrits in a bowl system vary, and just the blue little arrows show how it has to wash and go up against there and mix with the red cells. Key points to remember, you always have to choose a bowl size on the competitors. You got to figure out, well, not all of them, as you know, but we're salvaging a lot less blood nowadays. People are better at what they're doing. So a lot of people use small bowls, but you get in trouble, then you have to fill, wash, empty, fill, wash, empty. And so then you get a larger bowl, you don't get enough. You do partial bowls, your hematocrit's going to be lower, you're going to hemodilute more. Ours, one disposable does it for everything. And like I said, it can be very fast. Ochsner uses ours for, I don't know how many livers they do. They're the biggest liver program in the country. So we get the fat out of the blood on all our programs. You don't have to choose a program. I went pretty fast there, so it's fairly detailed. So you guys have any questions? I thought I put that up there. It's almost like looking out the windows when I came in here this morning. It was absolutely beautiful coming in. So. That boring, huh?
From the webcast, someone asked, from when there's high pressure and suction, there tends to be a pump failure error, and they asked, can this be attenuated with software change?
Yeah, I actually, if they're using our older device, that was a problem when we first started running because our pumps run a lot slower because we have 3 doing the job of 1. So it can't create a lot of vacuum because it runs a little bit slower at the beginning. I had offered, or suggested to Germany, maybe we could ramp that thing up right away first and then slow it down. On our new device, what happens is that blood pump runs retrograde and gets rid of the air going up into the reservoir. And the reason it does that is it primes that hematocrit sensor. So by doing that, we actually seal that pump then, and we have very little problems. I've run it at vacuum levels of 700 and haven't had a problem. So it's normally seen at the beginning of the case when that pump's dry, and it's trying to seal and so.
Also, is there any appreciable heparin left in the wash blood during cardiac cases? They're saying that some of the surgeons believe that blood still contains therapeutic amounts of heparin, and they don't want to use it. So,
I watched that talk on the TEG, and that was, I totally agree with everything you said. I think that was an awesome talk on how to use it. I did a lot of research on hemolysis. Anyways, not hemostasis. But anyways, our research shows we get out 99% of the heparin. Now 99% of what level, there still is some, but it's pretty insignificant. I actually, because I saw this phenomena when we were giving cell saver blood, competitors, everything. And it normally happens in heart cases. And I talked to one of these gurus on hematology and everything, and he says, when is it happening? So we tried to correlate it, and it looked like it was happening right after protamine. And so what was happening is that's when you're giving cell saver when you come off bypass. So they're looking up and they're seeing this red bag going in and they're starting to bleed. He was saying it's probably right after protamine's given, you get a little bit of platelet dysfunction, and that's when it happens. And he said that could explain it. I don't have a definite answer, but that's kind of made me feel better. But because there is very little heparin in the blood.
And also, what about the removal of bacitracin? Can CATSmart be used?
I hate to get into individual contraindications. It's not intravenous antibiotic, so any of that is not good. We're going to get out a high percentage of it. Now, how much is in there, you never know because you don't know. We get out 1%. So, from Vicinity's point of view, no, we shouldn't use it. But I know everybody does. I mean,
that's it. That's perfect.
Okay.
Thank you so much.